Nick Sarian.
I'm Stuart Day.
I'm John Thomas.
I'm Matt Roper.
And today we'll be discussing photovoltaic systems. And this is for Dr. Kate Davis's ECEN 340 class at Texas A&M University in fall 2019. So our structure for today's video is going through a solar panel, charge controller, which charges into a lead acid battery, which ends up needing to be converted to through a DC to DC converter, ultimately to our load.
So first of all, we have the standard solar panel, also known as the solar module, which is made up of a layer of silicon cells, metal frame, glass casing, which this one doesn't have, and various wiring components to allow the current to flow from the silicon cells. As you already may know, silicon is a non-metal with conductive properties, which allows it to absorb and convert sunlight into electricity. When light interacts with the silicon cell, it causes electrons to be set into motion, which initiates the flow of electric current. This is known as the photovoltaic effect, and it describes the general functionality of all solar panel technology. The photovoltaic process can be simplified into three main steps. First, the silicon voltaic cell absorbs solar radiation. Then, when the sun's rays interact with the silicon cells, the electrons begin to move, which creates a flow of electric current. Finally, the wires capture and feed this current into a charge controller.
Alright, and once that current comes from the solar panel into the charge controller, we need to clean up that energy so it can be stored well into a battery, specifically a lead acid battery. And the first big thing we need to do is handle how current enters the battery. The industry standard right now is a 3-stage charging cycle. The first stage, when the battery is at its lowest capacity, will allow full power from the solar panel to come through and charge the battery. At the second stage, we usually limit it to a lower percentage, half or less depending on where the points are set. And then once the battery is near full charge, we'll bring down the current going into the battery to 0 or trickle, just to keep it topped off. And on the load side of the battery, in the discharging, we just need to make sure that we don't over-discharge the battery, because most batteries for renewables will destroy once they drop under 20% capacity. And the main way we do that is we measure the voltage of the battery and cut off the load when it drops around 20% and wait until the battery gets charged up again to give energy back to the load. So now that the signal and power is cleaned up, we can start storing it in the battery.
And our battery is made up of three main components. We have a negative plate, positive plate, and electrolyte. Each of these plates have their own specific chemical components on them. And so when you go from fully charged to discharge, the makeup of the chemical components actually changes. And when you have that makeup going through the charging or the discharging, through discharging, you acquire your electrons that are equivalent to 2.05 volts per actual molecular equation reaction, and that's it.
And so finally, from the battery, to get to our load, if you have a load that isn't a 12-volt battery, like in the case of a steel lead acid battery, you need a buck converter, right? If you need to step down to a lower voltage, your buck converter or a step-down converter is a DC to DC power converter which steps down voltage while stepping up current from its input supply to its output load. It is a class of switched mode power supplies, SMPS, typically containing at least two semiconductors, a diode and transistor, although modern buck converters frequently replace a diode with a second transistor used for synchronous rectification, and at least one energy storage element, a capacitor, an inductor, or a combination. To reduce voltage ripple, filters made of capacitors, sometimes in combination with inductors, are normally added to such converters' output on the load side filter and on the input supply side filter. And for example, this is a buck converter featuring the TPS 54331 3-amp 7-volt 28-volt input step-down DC to DC converter, which is used currently in my senior design project to power a 3.3-volt input single-board computer. And so now that we've discussed the photovoltaic system from beginning to end, from the solar panel, which charges through a charge controller, maintaining charge for a lead acid battery, ultimately going through a DC to DC converter into our load. That is our photovoltaic system, and we'd like to say thanks and gig 'em.